Okay, so I think let's start Thien. So I think before Thien start his PhD presentation, I just have a few words to share about Thien. So basically, Thien going to have his overall presentation before submitting his PhD thesis next week. And after next week, I think in early July, Thien gonna start as a postdoc in our group also. And a little bit about him. So it has been like 3 years since he came to ANU to do his PhD under the supervision of Dan McDonald and myself. And during this time, he did an excellent job in exploring the characteristics of the passivating contacts for silicon solar cell and trying different ways to improve their performance. So basically, he showed himself as a very motivated and hardworking person, often stay in the lab until 7 or 8 p.m. writing. And besides his PhD project, he also have a lot of people with different measurement and sample preparation. So I'm sure we all appreciate his presence here for the benefit of our group. So now I just let Thien to share with our group what he has done over the past 3 years. Just go ahead, Thien.
Thanks very much, Hugh, for your kind introduction. Yeah, so I started my PhD in July 2018. So thank you everyone for attending this presentation today. This presentation is a summary about my PhD works on the characterization and defect engineering for polysilicon participating contacts in silicon solar cells. So let's start with the outline of my talk. So we will first start with an introduction and then the thesis motivations. Then we will jump into the two main parts of this thesis, will be the characterization and the defect engineering for the silicon oxide participating contacts. And finally, a summary and future work will conclude my talk today. Let's start with the introduction. So as you know that the polysilicon passivating contact technology is currently attracting a lot of research interest from the PV community. As you can see from the figures here, there's a lot of record devices efficiencies from, for example, here ANU, Fraunhofer ISE, and ISFH. So these all very high efficiency demonstrate the potential of this technology. On the other hand, there's numerous works on the solar cell fabrication, the working mechanisms or the transport mechanism, but less works on the characterization and defect engineering. That's led us to the motivation for the works in my PhD. So the device performance are strongly dependent on the structural surface morphologies and optoelectronic properties. So to a comprehensive understanding of these properties will have to improve the performance of the finished devices. Also, we know that the polysilicon films often contains both amorphous and crystalline phases, and the oxide interfaces with the polysilicon film and the silicon substrate often contains a very high level of defects. That lead us to the need for a hydrogenation treatment, and also some question arise that how effective these hydrogenation treatments on different polysilicon passivating contacts, and what are the underlying mechanisms of the different hydrogenation treatments. So let's explore all of them in this presentation today. Let's jump to the part one. So the first part here, we will do the characterization for the polysilicon passivating contacts. Firstly, we will study we will comprehensively study the morphology, microstructure, and doping behavior for different polysilicon passivating contacts prepared by different deposition methods. And then from this knowledge, we will move to two case study. In the first case study, we will characterize the Xc2 doped polysilicon passivating context based on the sputter silicon. And then in the next case study, we will characterize the p-type spin-on doped polysilicon passivating context using the boron glass solution and also the boron gallium mixing glass solutions. So this part here based on the 4 publication, 3 of them already published and 1 in preparation for journal submissions. So let's start with the first topic, a different polysilicon passivating context, the characterization of morphology, microstructure, and doping behavior. So this is the outline of the work here. We start with the introduction and then experimental details. We will compare the deposition rate from different methods, and then we compare the luminescence properties and hydrogen content, and then the doping behavior, microscopic structure, also the crystallinity and surface morphologies, and finally the surface passivation. As introductions, so you know that there are 2 main approaches for the deposition of the silicon films. They are chemical vapor deposition (CVD) and physical vapor deposition (PVD). Each resultant polysilicon film has its unique characteristic. Therefore, achieving consistent high performance passivating context requires an insightful understanding of the properties of the films across different deposition technologies. So let's start to compare. Let's start first with the experimental details. So for the sample preparation, we use 3 different deposition techniques here. They are sputtering, BCVD, and LBCVD for the silicon deposition. After the Xc2 phosphorus diffusion, the phosphorus silicate glass will be removed before any characterization. For the characterization, we will use a combination of these techniques here. Let's compare the deposition rate between the different deposition techniques. So as you can see from the figure on the right here, within the same method, the deposition rate is quite uniform. For sputtering, it is 2.6 nanometer per minute. It is 28 for PECVD and 1.4 for LBCVD. These are the deposition conditions for different techniques. So we observe that the lowest deposition is for the sample on LBCVD. On PECVD, it has the highest deposition rate. Meanwhile, on the sputtering samples, the sputtering techniques, we expect to see denser films. Note here that the rate is not necessarily representative of the industrial tools. Let's compare the luminescent properties and the hydrogen contents. We note here that the BL were captured at BL spectra captured at 80K using the 405 nanometer laser. For the edge deposited films from different deposition methods, you can see that on sputtering, there's extremely low intensity and there's no hydrogenated amorphous silicon PL peak, and also no high crystallized silicon PL peak, which indicates that there are little or no hydrogen inside the films, and the laser light mostly absorbed in the silicon films. Meanwhile, on the BCVD edge deposited film, we see there's a clear hydrogenated amorphous silicon PL peak, which indicate the film contains hydrogen. On LBCVD samples, we see clear crystallized silicon and also polysilicon PL peaks, and no hydrogenated amorphous silicon PL peak, which indicate here the films has some crystallized phase and little or no hydrogen. After the phosphorus diffusion at 830 degree, on sample shows no hydrogenated amorphous silicon PL peaks, which indicate all the hydrogen already diffused out of the films. And we see clear crystallized silicon PL peak and polysilicon also. So it indicates the films already crystallized after the high temperature diffusions. We note here that we see a distinct difference between the CVD methods and BVD methods. which is the appearance of the end diffuse peaks located at around 1160 nanometer. So that's in case on the BECVD and LBCVD samples, there's strong indiffusion to the crystallized substrate. Meanwhile, on the sputtering sample, that's very minimal. This can be checked with the ECV profiles in the next slide. Let's compare the doping behavior between the different methods. So for sputtering, we see higher phosphorus concentration inside the polysilicon film. On LBCVD and BECVD profiles, we see higher indiffusion in the crystallized silicon substrate. That's verify the BL results I mentioned before. On sputtering and BECVD, in the crystallized silicon substrate, we see similar doping profiles. Meanwhile, for LBCVD, we see a strong dependence of the indiffusion on the initial thickness. Also, I provide here the sheet resistance plot to confirm the ECV profiles. Let's compare the microscopic structure here. The thickness of the films can be observed by the low magnification images. As you can see here, we use three similar techniques for sputtering and BECVD, but for LBCVD, 37 here is the maximum thickness. The oxide interface can be seen from the figures on the bottom row here as amorphous strips. And the crystallized silicon and polysilicon can be identified by the phase contrast on the crystallized silicon substrate. That is uniform crystallized phase. Meanwhile, on the polysilicon film, from both three methods, we see it's mixed phases of amorphous and poly crystallized phase. And also from here, we can say the crystallized phase seem growing from the oxide interface rather than from the surface. Okay. Let's compare the crystallinity between the different methods here. So for the sputtering and BECVD, we can see that increasing the diffusion temperature shows slightly increment in the peak intensities, which indicate that there are some increment in the degree of crystallinity. For similar techniques of the BECVD and sputtering films, we see that the peaks are nearly identical, which indicate the two films has a similar degree of crystallinity. For LBCVD, we see quite low peak intensities. This is the thickest film we got, and the peak intensity is quite low. To calculate to quantitatively compare the crystallinity, we calculate the grain size from the different XRD results here, and we found that the sputtering has the smallest size. Meanwhile, on the LBCVD sample, it has the largest size of the grain. These results can be verified by the AFM results in the following slides. Let's study the surface morphologies from the different samples by different methods here. On the substrates, after the TMAH and HF or by after the focal diffusion or oxide growth, we see that the surfaces are smooth and the diffusion and oxidation have no effects on the substrate surfaces. Meanwhile, after depositing the silicon film, we see on sputtering and BECVD, the surfaces are relatively smooth. But on the LBCVD films, we see some crystalline peaks, which indicates there's some crystalline phase inside the LBCVD films. After the phosphorus diffusions, on sample shows the high density of crystalline peaks here, but there's a difference in the size, shapes, and densities. So based on the image here, we extract the size of the size and the densities of the peaks, and we found that for sputtering, it has the smallest size, and highest density. Meanwhile, on LBCVD, it's the biggest size and the lowest densities. To quantitatively compare the surface morphologies between the different samples here, we extract the surface roughness RMS and the result, so that for different crystallized silicon substrates, it has the smallest RMS. Meanwhile, increasing the diffusion temperature, so increment in the RMS for all technologies. And the BECVD, it has the smallest RMS compared to the ABCVD and sputtering. With the surface passivation, we can see here on the figure here, we see for LBCVD sample, increasing the thickness shows improvement in IBOC, and it can reach 720 millivolt without any hydrogenation for the LBCVD sample here. So the reduction of IVOC with reducing the thickness of the film may be due to the auger recombination, and actually it's in fact it's correct, because recall to the ECV profiles before, thinner film shows higher in diffusion. So to simulate that's auger recombination, we did a simulation by ETNA2 program, and in fact, as you can see here, reducing the thickness of the film shows increment in the auger recombination J0. Okay, for BECVD and sputtering, when we're increasing the thickness, shows the reduction in IVOCs for the sample less than 890 degree diffusions. For 890 degree diffusion, the trend is reversed. So we note here that the context has not have not optimized yet, so we should not compare them directly, and the optimization should be done independently for each technique. As the conclusions, so we saw that the BECVD film has the highest deposition rate, smoothest surfaces, and LBCVD, it has the lowest deposition rate and roughest surfaces. On the edge deposited silicon films, sputtering and BECVD contains only amorphous phase. Meanwhile, on LBCVD, it contains both amorphous and crystalline phase. After the phosphorus diffusions, on the polysilicon films contains both amorphous and crystalline phases. With the XRD results, we can say LBCVD polysilicon film, it has lower degree of crystallinity compared to the other methods. With the ECV profiles, we see that LBCVD and BECVD samples show higher in phosphorus in diffusion rate. And finally, different passivation performance responses lead to the need to perform a separate optimization for each silicon deposition methods. Okay, so let's continue to the next case study here on the sputter polysilicon characterization. This is the outline of the talk of this part. So we will go with the introduction, then experimental details, and deposition rate and crystallinity, and the PL spectra, that's the optoelectronic properties, PL and FTIR, and doping behavior, and contact resistivity, and surface passivation, based on our comprehensive understanding from the previous topic. So let's continue with the introduction here. So we know the typical methods to form polysilicon passivating contacts. They are CVD, I can list a few here: BECVD, LBCVD, atmospheric CVD, and hot wire CVD. Also, for the BVD methods, we often use electron beam deposition and sputtering. So sputtering will be the focus of this work here. About the characteristic of different methods, in CVD, it often requires toxic gaseous precursors at high temperatures, and it will require extra safety measure. For BVD, it's often safe, and it can be performed at room temperature. About the property of the sputter film, previous work from Diyan published in APL 2019 already reported a very good silicon solar cells efficiency with efficiency of around 23%. With in situ doped polysilicon passivating contacts. So in this work, we will do another different things that we do ex situ doping for the polysilicon and observe the dependence on the pressure. By separating the silicon deposition and doping, we can evaluate the effects from different processes on the final device. So this is the experimental details. So for we will use the 100 ohm wafers, and then we deposit amorphous silicon layer by sputter, and there will be 3 different temperature for the ex situ boron diffusion. For the hydrogenation, we will use forming gas or forming gas anew or allox and forming gas anew. These are the combination of characterization techniques similar to previous works. Let's start first with the deposition rate and crystallinity. As you can see from the figure here, the deposition rate decrease with increasing the pressures. Also for the TM images here, on low pressure samples, we see bigger crystal size. With the GI-XRD results here, we can see that the peak intensity increase here maybe due to the difference in the techniques. It's not different by the pressures. About the optoelectronic properties, the figure on the left here presents the amorphous silicon PL, and on the right, that's the PL of the sample after the boron ex situ boron diffusions. So as we can see from the figures that similar to previous work, we say there's no hydrogenated amorphous silicon PL peaks in the S deposited films. So it indicates little or no hydrogen, and it's extremely low intensities of the PL, which indicates the laser light mostly absorbed in the amorphous silicon layer. After the diffusion, we see clear soft crystallized silicon peak and polysilicon peak, which indicates the film already crystallized. About the FTIR absorption spectra, so on the S deposited samples, we see the silicon hydrogen absorption peaks, which arbitrarily say it contains hydrogen. So this may be due to the involvement of hydrogen during the chemical oxide growth. But either way, after the boron diffusion, there's no silicon hydrogen peaks, so there's no trace of hydrogens after the diffusion. About doping behavior, so for samples larger than 1.5 milliliter, we see the doping profile quite similar in the crystallized silicon substrate. But for the 1.5 milliliter samples, the thick polysilicon film, there's more indiffusion of the dopants inside the crystallized silicon substrate. There's possible reasons for that. That's maybe due to the different crystallinity and density between the different pressures, and maybe due to the oxide stoichiometric. Also, the high kinetic energy when the silicon atom collide with the oxide may affect, and also probably less boron segregated in the inactive form. Inactive form may cause that. About the contact resistivity, we can say that the contact resistivity is low, and it's around 4 milliohm centimeter square for for the sample at 1.5 milliliter. In here, compare with the in situ dop from Diyan. From Diyan, we see that for similar thicknesses and pressure, we see similar ROCE. For similar thickness, here is 60 and 70 nanometer. The ROCE different with pressures. And for similar pressures, the ROCE varies with the thicknesses. Continue with the surface passivation. Compare with the in situ dop from Diyan and he performed a nitrogen annealing after finish his sample. So in here we use the forming gas and allox forming gas. So we see similar J naught for 2.5 millitorr sample after the forming gas anneal. For the sample from 1.5 to 2.5 millitorr, we see a J naught increase after the allox forming gas, and it can reach the best J naught of around 9 femtoam per centimeter square, even lower than Dian works. And for the 4 to 5 millitorr samples, we saw some inconsistency in the performance. Okay, so as conclusions, here we see that lower pressures use thicker and denser films with the same sputtering time, and due to higher deposition rate. The BL spectra of the S deposited film, there's no hydrogenated amorphous silicon PL base, confirming the absence of hydrogen. But the FTIR spectra of the S deposited films, it shows the silicon hydrogen peak. It's likely due to the residual hydrogen incorporated during the chemical growth of the oxide. And finally, the resultant polysilicon passivating contact shows good initial J naught of around 24 femtoam per centimeter square, and after hydrogenation, that is 9 femtoam per centimeter square. So let's finish the case study 1. Let's move to the case study 2. The characterization of boron and gallium boron spin-on doping for polysilicon passivating contacts. Start with the introductions. So typical Xc2 doping methods for the polysilicon passivating contacts fabrication are gas diffusions, ion implantation, or using the liquid dopants. And here it can be screen printing, inject printing, or spin-on doping. So the spin-on doping will be the focus in this work. About common type of B-type dopants for polysilicon passivating contacts, we often use gallium and boron. Some characteristic of boron and gallium can be listed here. So for boron, we see low diffusivity in silicon oxide. It spire up and crack up the oxide during the annealing. It has smaller atomic radius versus the silicon. So it's called lattice strength or the defect engineering. That often lead to high recombination. For gallium, it has 6 orders of magnitude higher diffusivity in silicon oxide. That's versus boron at 850 degree. And it's not pile up, not form defects with silicon oxide interface. It's not crack the oxide also. And it has similar atomic radius to silicon, also with low solubility in crystallized silicon. Gallium dope shows higher contact resistivity compared with boron dope, but it had better performance. So in here we can say boron spin-on doping, it can be possibly be an alternative to the traditional boron diffusion. And the co-doping of gallium and boron can possibly bring the advantages of both to the passivating contacts. So let's explore in this case study here. So this is the outline. We will study the surface passivation, doping behavior simulation, and contact resistivity. So this is the experimental details. We use the intrinsic polysilicon sample from Jinko, and we use TOM structure for the characterization of contact resistivity. So as you can see from the figure here for the surface passivation, we first study the effects of driving temperature to the passivation. So as you can see that increasing the temperature shows increase in IVOC on the S and new sample, and it's reached the maximum at 950 degree with an IVOC of around 690 millivolt. Similar trend also observed in the sample after hydrogenation by alloxanitrile forming gas. Its maximum IVOC at 950 degree and reach a value of 720 millivolt, which is quite high. So this is the optimal temperature we choose to study the effects of dwell times. We varies the duration of the annealing for a fixed temperature of 950 degree. So we see that the dwell time show less influence on the IVOC with the delta IVOC around 10 millivolt here, and longer dwell time shows increasing IVOC, but it's maximum at around 60 minutes. Let's study the doping behavior. So we also do the same for 1 hour annealing for different temperature and annealing at 950 degrees for different time durations. So we can see here the concentration of boron inside the polysilicon films quite uniform at around 10 to the 20 for the sample anneal larger than 900 degrees. For the 850 degree, we see significant lower boron concentration is around 5 to 8, 10 to the 19. So we see here higher temperature, longer dwell time, so higher indiffusion rate in the crystallized silicon substrate. And longer dwell time shows more boron concentration inside the crystallized silicon substrate, but the boron concentration in the polysilicon film still the same, regardless of the thickness. Okay. So we simulate also the recombination parameters from Auger recombination and the total recombination with the ETNA2 program. As you can see from the first figure here, so increasing temperature, increasing the driving temperature, so significant increment in the J0 Auger. And prolong the dwell time, so similar trend, but little change. Also, the forming gas annealing shows slight effects on the total J0, and little effect on the J0 Auger because the doping density is not affected. So we provide some seed resistance from the simulated and 4-bond probe measurements to confirm the trend of the J0 here. For the contact resistivity, we see as shown in the figure on the right side here, it's low and it's in the range of 1 to 10 milliohm centimeter square. And as you can see, increasing the diffusion driving temperature, so significant increment in the J0, in the rho C. There's possible reason for that is at higher temperature, higher than 900 degrees Celsius here, the oxide becomes denser. It might block more boron diffusion into the crystallized silicon substrate. Also, the oxide may increase in the electrical resistance. The seed resistance measured by 4-bond probes and measured by the TOM and the simulated results agree well, the trend, So as conclusions, in here we explore the impact of driving temperature, dwell time, and the polysilicon thickness on the performance of boron spin-on doping passivating contacts. And for all polysilicon thicknesses, 950 degree for 60 minutes is the optimum condition for passivation. And after the hydrogenation, we can reach an IVOC of around 720 millivolt with contact resistivity as low as 5 milliohm centimeter square. And prolonged annealing time shows slight increase in IVOC and stronger in diffusion. And finally, the polysilicon techniques here present negligible effects on the recombination. Let's continue with the case study 2.2, the gallium boron co-doping with the spin-on methods for polysilicon passivating contacts. So we will study surface passivation, contact resistivity, the doping behavior, and the PL from the gallium dope samples. For the IVOC sample, we prepare the silicon film by the LBCVD in our lab. And we use allox nitride for hydrogenation. For the contact resistivity measurement, we use a cost and struct methods to extract the contact resistivity. First, with the surface passivation. As you can see from the figure on the right here, on the S and new sample, that's the gray color. So we see increasing the percentage of gallium in the gallium boron mixing solutions. We see a decrease in IVOC, and each percentage of gallium has its optimum temperature. So for the 100% gallium sample, we see IVOC drop to a very low value of around 610 millivolt. For on driving temperature, after the hydrogenation, the solid curve, solid line here, we see IVOC improve significantly with average of around 700 millivolt for on sample less than 75% gallium, and it's around 720 millivolt for sample with 100% gallium. So as you can see here, the presence of boron in the boron gallium mixing solution seems limits the improvements of IVOC after the hydrogenation. For the contact resistivity, when we're increasing the driving temperatures, it shows decreasing in the contact resistivity. For the 1000 degree annealed samples, the sample has low contact resistivity in the range from 4 to 60 milliohm centimeter square. Increasing the percentage of gallium shows increment in the ROCE. For the 100% gallium sample, annealed at 900 to, that's the black, 900 to 930 degree. We see the low temperature lead to a very high contact resistivity, so we can, it's immeasurable for the next two data here. For the 930 to 960 degree annealing samples, we see IVOC around 700 millivolt, and together with a ROCE around 10 milliohm centimeter square, which is relatively good passivation. So we choose 960 degree is the optimal temperature for the next characterization experiments. For the doping behaviors, as you can see from the figures here, we use ECV to detect the maturity, the active maturity carriers. Meanwhile, we use SIMS to detect on active and inactive dopants and dopant type also. So the first two figures is the SIMS profiles, and the next figure here is a combination of SIM profiles, total SIM profiles from boron and gallium, and plot together with the ECV profile. So the gap between the two lines for each percentage of gallium is the amount of inactive dopants. So as we can see from the figure A, increasing the gallium percentage, we see higher concentration of gallium in the polysilicon and also in the crystallized silicon films. Meanwhile, for the boron SIMS profile, we see boron diffuse more deeply into the crystallized silicon substrate than the gallium. For the 100% gallium sample, we see very low active dopant concentration here compared to the other percentage. To quantitatively compare the amount of active and inactive dopants, I also plot here the percentage of active and inactive for the polysilicon and also the crystallized silicon substrate. And we found that the number of inactive dopants is higher than the active dopants, both in the crystallized silicon and polysilicon film. Finally, the BL spectra from the gallium doped sample shows on the intrinsic LBCVD poly PL, we see very low intensity of crystallized silicon peak. So the laser light is absorbed mostly in the silicon films. similar to what we have seen in the previous slides. For the S-driven in PL sample, we see clear crystalline and crystalline silicon and polysilicon PL peaks, which show some surface passivation, the red curve here. After the hydrogenation by allox nitride and forming gas, we can see that the crystalline silicon and polysilicon PL peaks increase significantly, which show the improvement in the performance. We noted that the IVOC increased to around 720 millivolt here. So for conclusions, in this work, we study the impacts of gallium missing volume percentage in the gallium boron solutions on the performance and optoelectronic properties of the contacts. And independent of the gallium boron ratio, we can see that surface passivation after hydrogenation improved with the IVOC larger than 700 millivolt. And the ECV and SIM profile shows the active and inactive percentage inside the films. And finally, the PL spectra shows the evolution of the gallium doped samples. So let's this is the end of part 1. Let's summarize what we got so far. So we have seen that a combination of different characterization techniques has been used to comprehensively study the various properties of the different polysilicon passivating contacts, from the structural surface morphologies and optoelectronic properties. Using the knowledge obtained, the different properties of the sputter films deposited at different pressures were studied in the first case study. And the different properties of the passivating contacts formed by the spin-on doping were also investigated in the second case study. So now let's jump into the next part. That's the defect engineering for polysilicon passivating contact by means of the hydrogenation treatments. So this part divided into three topics. The first topic will be an initial studies on the hydrogenation of the phosphorus doped polysilicon films for polysilicon passivating contacts. And then in the next topic, I will extend the studies for different polysilicon passivating contacts using different polysilicon films formed by different BCVD amorphous silicon deposition condition, the substrate types, surface morphologies. Here is texture or planar, the doping types of the substrate, and doping also the diffusion of the polysilicon film and the diffusion temperatures. Then finally, I will study the hydrogenation effects on different by different cupping layers and come up with some proposed mechanisms for the hydrogenation. So let's start first with the initial study on the hydrogenation for phosphorus doped polysilicon passivating contacts. I will show here the experimental details, evolution of the PL, FTIR spectra, and the surface passivation. As you can see here from the experimental details, the sample were doped by phosphorus at 100 degree, 30 degree, and then it's annealed in forming gas for 30 minutes at 500 degree, and at stage 3, and silicon nitride layer were deposited on and annealed in forming gas. And at stage 4, the dehydrogenation step, we will anneal the sample in nitrogen for 600 at 600 degree for 2 hours. So let's investigate the evolution of the PL versus different processing steps as stated before. So in the S-diffuse PL in stage 1, we see that the crystallized silicon and polysilicon peak is quite clear, the green curve here. After the forming gas anneal, at stage 2, the PL spectrum still the same, very similar to stage 1. After another silicon nitride forming gas anneal at stage 3, we see clear hydrogenated amorphous silicon. That's the blue curve. And also the peak of the crystallized silicon and the doped polysilicon increase. which indicate the crystallized silicon substrate and the doped polysilicon films anode passivated. So it's a higher big intensity here. So it's indicate a hydrogen anode incorporated to passivate the polysilicon film and crystallized silicon substrate. After a dehydrogenation step, like step 4 here, we anneal the sample at 600 degrees for 2 hours. We see the spectrum similar to stage 1 and stage 2, which indicate there's no hydrogen inside the films. Using the FTIR methods technique, we can track the silicon hydrogen stretching modes. So in fact, here we see on either diffusion temperature, we see clear silicon hydrogen peak on the sample hydrogenated by silicon nitride. For the surface passivation with different processing steps, as you can see on the right figure here, at initial stage 1, we see some passivation with IVOC of around 680 to 710 millivolt and lifetime around 1 to 1.5 milliseconds. Relatively good passivation. But after the forming gas anew at stage 2, we see the IVOC and tau F increase a bit to around 4 to 4.5 millisecond. No, that's around 720 millivolt. After the silicon nitride and forming gas at stage 3, the IVOC and tau F increase significantly to the maximum value here. But after the hydrogenation step at stage 4, the IVOC and tau F decrease significantly, dramatically, I would say, even lower than stage 1, which indicates all of the hydrogen it fills out of the films and no passivation at all. So for conclusions, we identify the significant hydrogenation effects in the bulk of the phosphorus doped polysilicon layer. And after the hydrogenation, we see clear hydrogenated amorphous silicon PL peak and silicon hydrogen FTIR peaks. This can be used to verify the presence of hydrogen inside the films. And on the passivating context shows improved performance after hydrogenations. For details discussion and results on this, please check my paper published in ACS AMI in 2019. So in the next topic, I extend the studies on hydrogenation for different polysilicon passivating contexts. We start with experimental details and the surface passivation for planar and texture, and then we study some PL and TEM image of the texture samples. This is the experimental details. We use anti 1 ohm centimeter wafers, also p-type, like different substrate types, different substrate resistivity, and also we deposit the silicon film at different temperatures. For the diffusion, we use Boko and Poron diffusions, and for hydrogenation, we use silicon nitride and forming gas anew in combination with different characterization techniques. So here, so after the hydrogenation, we can see that either for phosphorus doped samples or boron doped samples at different deposition conditions here for the amorphous silicon films, and even different diffusion temperatures, different substrate type and P. So after the hydrogenation, on tau F and IVOC are improved. It's also improved for the texture samples with different substrate resistivity. We try to capture the BL of the texture samples after the before and after the hydrogenation, and there's some significant difference compared to the case of planar samples. So on the texture samples, we saw the BL spectra shows minimal hydrogenated amorphous silicon PL peak, after the hydrogenation. This may due to so we did some TEM image of the pyramids, and we found that edge area has disrupted silicon oxide interface. Also, the peak area has no clear boundary between the polysilicon film and the crystallized silicon substrate. So when we shine the excitation laser on the sample, all the carriers generated inside the polysilicon just injected to the crystallized silicon substrate. That's explain why we see minimal hydrogenated amorphous silicon pure peak here. So for conclusions, after the hydrogenation, the passivation on improved regardless of the initial condition, and the PL of the polysilicon passivating context on textured surfaces, so minimal hydrogenated amorphous silicon. But hydrogenated amorphous silicon and also polysilicon PL peaks, likely due to the disruption of the oxide interface at the edge and the peak of the pyramids. For details discussion and results, please check my paper published in ACS AEM in 2019. Finally, we studied the hydrogenation mechanisms of the passivating context by different capping layers. So this is the outline. We will study the BL before and after BL of the sample diffuse, and then we study BL and FTIR after forming gas anew and silicon nitride and alloys. Then we will study the effects on if we deposited another silicon nitride forming gas on the pre-hydrogenated by forming gas or alloys forming gas, and we come up with some proposed mechanisms and can verify the result by SIM profiles. So this is the experimental details. We in here for the hydrogenation treatment we use forming gas anew with or without the presence of the electric layers. And before the characterization, we will remove the dielectric layers. So the BL before and after the dopant diffusions, as you can see from the figure here, before diffusion, we see, I just repeat a bit about the work before. So before diffusion, we see clear hydrogenated amorphous silicon PL peak located at around 900 nanometer. And there's no crystallized silicon PL peaks here. But after the high temperature diffusion, we see clear crystallized silicon PL peak located at around 1125 nanometer. The polysilicon PL peak in the range of 1300 to 1500 nanometer, and the hydrogenated amorphous silicon PL peak disappear. So we can use this phenomenon to track the hydrogen inside the films. Let's start first with the hydrogenation by forming gas anew. This is the BL spectra and the FTIR spectra captured from the sample before and after the hydrogenation. So we can see that there's nothing changed, but we noted that the IVOC is increased after the forming gas anew. Interestingly, there's a significant difference between the sample at height with high base substrate resistivity and low substrate resistivity. Continue with the hydrogenation with silicon nitride and forming gas anew. So this is the BL spectra and FTIR spectra also. So after the hydrogenation, we see clear hydrogenated amorphous silicon PL peak, and the BL, the polysilicon BL peak also increase. We see silicon hydrogen stretching mode at 2100. Note here that the IVOC also increased significantly after the silicon nitride and forming gas anew. How about the hydrogenation with the alloys and forming gas? So this is the BL spectra and the FTIR spectra. So after the hydrogenation, we see that they are similar to the hydrogenation with forming gas anew. There's nothing changes. We note here that the IVOC increase and it's more significant than the case for forming gas anew. Okay. So what if we do another silicon nitride forming gas on top of the sample already hydrogenated by forming gas or the ALOX forming gas? So this is the BL and FTIR spectra captured from those samples. So for BL spectra, we see clear hydrogenated amorphous silicon PL peak located at around 800 to 1000 nanometer here. And for the pre-ALOX sample, for the pre-ALOX forming gas sample, we see higher BL intensities, the black curve here. For the FTIR spectra, we see clear silicon hydrogen modes on the hydrogenated sample, and the pre-ALOX sample shows even the silicon hydrogen, the dehydrized silicon hydrogen here. So which indicates higher amount of hydrogen already injected into the films. We noted also about the changes with the IVOCs. So after forming gas anew and then after ALOX forming gas, there's significant increment for the forming gas pre-forming gas anew sample. Meanwhile, for the pre-ALOX sample, it's degrade. Any hypothesis for the PL and FTIR here? So yes, we come up with some probable mechanisms here. The ALOX and silicon nitride, it has different association with the hydrogens. In the case of ALOX, it forms complexes and it's not passivated amorphous silicon dangling bonds. Meanwhile, on the silicon nitride case, both is passivate and form passivated dangling bonds and it's form complexes. So in the case of pre-ALOX, there will be more hydrogen from the second hydrogenation to passivate the dangling bonds, which explains why there's higher amorphous silicon hydrogenated amorphous silicon PL peak and dehydride peak here. To verify the result before, we did some seams measurements, and we see that after on treatments, there's significant hydrogen concentration inside the polysilicon film. And there's similar hydrogen concentration for the sample or ALOX with ALOX forming gas, the red curve, and forming gas and ALOX, the green curve here. It has similar concentration of hydrogen. We know that the ALOX and forming gas here did not show any BL or FTIR peaks. Meanwhile, for the sample ALOX and forming gas and then silicon nitride and forming gas, we see higher concentration of the in the book and the polysilicon film, and we noted that the IVOC reduced. So there's two possible reasons for this degradation, either by the plasma or by too much hydrogen injected into the film. So to verify that, we did another silicon nitride forming gas, and in fact the passivation is still the same. So the degradation by the plasma is the main reason for this degradation. Okay. So as conclusions, we saw the effectiveness of the different hydrogenation treatments and hydrogen on the sample hydrogenated by silicon nitride and forming gas. We see a clear PL peaks from hydrogenated amorphous silicon and FTIR silicon hydrogen peaks. And there's no hydrogenated amorphous silicon PL peak and silicon hydrogen FTIR peaks after the hydrogenation by forming gas anew and ALOX forming gas anew. Finally, the different capping layers cause different association of the hydrogen with the amorphous silicon phase. So this is the end of part 2. Let's summarize what we got so far. Initial studies on the hydrogenation on X2 phosphorus doped polysilicon passivating context demonstrate the effectiveness of this treatment. Extended studies on the hydrogenation on different polysilicon passivating contexts, different in substrate resistivity, doping type, diffusion temperatures, diffusion types, surface morphologies, and amorphous silicon deposition condition. Also shows the improvement in performance regardless of the initial condition. And finally, the studies of different hydrogenation treatments using such here forming gas and new silicon nitride forming gas and allox forming gas lead to the proposed mechanisms for different techniques. So to summarize the thesis and future works, we can say in this work we're exploring the various properties of the different polysilicon passivating contacts from the structural surface morphology and optoelectronic properties. And secondly, we're engineering defects inside the passivating contacts by means of hydrogenation treatments. For future works, some possible future work can be arise from this thesis is the solar cell fabrication using the different liquid dopants and also different dopant types, and the optimization of hydrogenation process and the electric layers. Also, we can try to understand the effects of different hydrogenation on hydrogenation treatments on different polysilicon films, and also the incorporation of hydrogenation treatments to mass production of cells. All right, thank you everyone for your attendance and your attention to my presentation. If you have any question now, please.
Okay, thank you very much, Thien, for the presentation. So do we have any question for Thien? So
I can start. First of all, yeah, great work, a lot. It's impressive how much work you did within this time frame. You did a lot of different techniques for polysilicon and analyzed them there, so you should get a good understanding of which ones are the best or what suits best. So my question would be, if you get now the task, make a highest efficiency cell or make a high efficiency cell by yourself in our laboratory, which technique would you go for, or what process flow would you follow?
Yeah, as you can see from the works here, like there are significant difference between different methods and different hydrogenation methods to improve the performance of the film. So I would say for each method, we can always optimize the performance and come up with a high efficiency cells. And it depends on the skills of the people working on the fabrication instead of the choosing of, I mean the choose of different of which techniques is the most suitable for highest efficiency cells, I would say. Yeah.
Okay, so I just have a question, like just follow-up question from Joshua. So like you talk a lot about hydrogenation, but like in summary, let's see, if I have a polysilicon dope, phosphorus dope polysilicon film,
yep,
and I want to do hydrogenation to improve its performance. So what is the best one? I just give you the sample and then I say just choose the best hydrogenation process to improve the best, to get the best performance. But that's what would you recommend? Forming gas, anneal, allox, silicon nitride, or combine both of them?
Yeah, I mean it's depending on the application we want, but I would say if we can use silicon nitride and allox stacks together to provide a best passivation. Again, it's depending on different application you want to do. From like forming gas anneal can provide some hydrogen in different type with the electric layers, like atomic hydrogens. So yeah, I would say it depends on the application you want to do. Yeah.
Okay. Right. Thanks, Thien.
Yeah.
So, do we have any more questions for Thien? No? Okay, so if there's no...
I can ask one?
Oh, yeah. Kelvin.
So I think for the hydrogenation studies, I think you mentioned that I'm actually quite curious why sometimes you observe that for hydrogenated sample, the amorphous lipid was disappear, right?
Yeah.
So I think there's 3 cases. One that you say that so basically what you say in texture sample you should not be able to detect anything because the carriers generated in the amorphous can be diffused into the substrate, right?
Yeah. Yeah.
And do you think that might happen a bit on your other example, well, on the aluminum oxide case?
I would say like on the aluminum oxide samples, planar samples, and so we did the same sample for nitride and allox, and we measure on nitride and we see clear peaks, but
Okay.
like on the same sample with allox, there's no peaks at all. So I didn't expect like the carriers from the allox participated samples just go to the substrate. Is that what you mean?
Yes. Okay. Yeah. And I guess in that case, would you expect on the texture sample, the fact that you don't see the amorphous circuit is due to the fact that there are some complex formed in the amorphous circuit?
You mean for on texture samples?
Yes.
I mean
The
the TEM image also like localized, so I don't know how because the laser light is around diameter is around 5 microns. It's pretty big, and then the peak of the pyramids here. So it's assumed that all of the peaks may have the disrupted oxide layer. So I expected on the texture sample will have minimal hydrogenated amorphous silicon PR peaks. Yeah.
Okay. And those are with the same nitride, right?
Yeah, the same nitride.
Okay. Okay. Thank you.
Thanks, Kevin.
Okay, so any last minute questions for Thien? I saw it's over 1 hour already. So, okay, so if there is no more questions for Thien, I think let's finish the presentation today. And thanks a lot everyone for joining Thien's presentation. And let's wish him all the best with his thesis writing. He's still correcting his thesis.
Yeah, thanks everyone a lot for your attendance today.
Okay, bye everyone.
Bye everyone.
I think let's stay a little bit. So let's chat a little bit about your thesis. Yeah, just wait.
Congratulations.